should be almost second nature how to do that. What are the three things we need for the equation of a tangent line? The x, y, and the m, right? So what is the x that we're looking at? What is the y? How do you know? So y plus 1 equals m times x minus 1. And I need the m. Well, does it just give me m for x equals 1? No, but can I find it? As dy dx, I do need to plug in both the x and the y. So my dy dx at x equals 1, this is the notation for dy dx at equals 1, is 3 times negative 1 squared plus 1 over negative 1 squared plus 2. So 3 on the bottom, 4/4. So tangent line, you need x, y, and m. That one's not too terrible. We had to do a little bit of work. We had to make sure we were on the right x value. Other than that, it wasn't too terrible. Now, I need to find whether this has a maximum, minimum, or neither at x equals 0. Well, I know the derivative is 0, but what else do I need to know if I have a maximum, minimum, or neither? I have two options. Good, I could do a first derivative test. To do a first derivative test, I would need to know a point, the slope on the left and the right of 0. I can find the slope on the right of 0, but I can't find the slope on the left. So the first derivative test fails me here. I don't have enough information to do the first derivative test because I don't know a y value to the left of 0, and I need an x and a y. This is a brilliant AP problem forcing you to use the second derivative test, which makes this quite a bit of work because I then have to find the second derivative, which means I have to do the quotient rule. Low d high fix y dy dx over 2, whoops, hold on. O d high minus high d low over low squared, which is y squared plus 2 squared.
I have a question.
Yes.
Okay, so you said that you couldn't figure it out because you didn't have a number that was to the left. Can you not just plug in a number? Because it gives you the first derivative.
What would you plug in for y? So I get here, I need the second derivative at where? Where do I need to calculate the second derivative at 0? So I need the second derivative at 0. And you could even say x equals 0 and y equals 0, which is important to know, isn't it? I know the first derivative at 0 is 0, right? This is going to go pretty fast, isn't it? Because everything's 0. Not everything, but you know what I mean. 0 plus 2 times 0 plus 1 minus 0 over 0 plus 2 squared. It wasn't as bad as it at first glance appeared that it would be. So I get 2/4, which is 1/2. All I need to know is that that is positive. So that's greater than 0. means it's concave up. Therefore, I have a relative minimum. Now I need to say that. This is your worst enemy on the AP Calculus exam. Justify. So, I'm going to try to justify what I just concluded. So, a couple of things I had to know. First, f prime of 0 equals 0. Why do I need to say that? Why is it important? For the second derivative test, I first have to know that I have a critical point, right? Second derivative point says if I have a critical point and the second derivative is positive, therefore, y'all know the 3 dot therefore, since the first derivative is 0 and the second derivative is greater than 0, there is a relative minimum of 0 at x equals 0 by the second derivative test. Now, this by itself would not be enough to get full points. They do need to see your work up there that you did the second derivative, but this would be where your justify points. To justify using a theorem, you practically state the theorem in the specific case that you have. Any questions about that one? The last thing we're going to do is go finish the last problem we were doing yesterday. We were done. We just have to graph it. Okay? We were a little concerned about that point of inflection at -1/2. And I did a little closer inspection of the graph after y'all left. And it turns out we picked up something that we wouldn't have seen by just using the calculator. If you do zoom in on that -1/2, you can see a change in concavity there. So I wouldn't have noticed it by just using the calculator. But then if I zoomed in on it, you could kind of look at that spot. You could see a change in concavity. So it's kind of interesting. Something that we noticed. So we had a change in concavity at -1/2. What did it change from? I think it was concave down and then concave up. So it had just a little, and again, you wouldn't see that just by looking. Now, if you look close, you will. But it was a slight change in concavity. And then at 0, the derivative was undefined, right? Mm-hmm. What makes a derivative be undefined? A cusp or a sharp corner of some sort. And then we went to 0. And then we were still concave up after 0. And that concavity that didn't change is kind of what caused that cusp. Do we have x-intercept at 5/2? 2.5. So it did something like this. Any questions about that? So putting down all of the information that we had on paper. So we had concave down and then a concave up, but then it stayed concave up, and that's kind of why we had that cusp instead of a smooth curve. And the derivative was undefined. What was this point, this minimum? 1, -3. At 1, -3, we had our minimum value. It was smooth at 1, -3. Okay, any questions about that one? Didn't we finish it except for putting the graph down? Mm-hmm. All right. For the rest of class, you can ask me test questions. You can ask me other questions. Today is a work day. Tomorrow we'll still have time for some questions, but we're going to play a matching game. you look at the first and second derivatives on cards and match it, you'll make some good conclusions tomorrow. So tomorrow will be a full work day like today is. All the homework is due on Thursday.